This is where we were in our last video. We looked at the difference between the differential and the derivative, where we said the differential is a small change, but the derivative is a small change of one variable compared to a small change in the other variable, right? Example, dy by dx means how much is y changes as changing as x changes. And we looked at what happened here. If you consider the cylinder with radius and height, you can lock r to make it a constant and change h, and find the partial derivative delta v by delta h. You can lock h and make r change, so you find the partial derivative of v with respect to r, that's delta v by delta r. Now, suppose you consider both of them changing at the same time. What would happen? Let me just erase these things and see how we argue the situation when both of them change at the same time. Alright? Now, here we have, well, what was it again? Delta v by delta h was pi r squared, and delta v by delta r was 2 pi r h. Alright? Remember that. Now, both of them are changing at the same time. They're changing simultaneously. So therefore, if you consider r changing, then r would become r plus delta r. Now notice this delta is a different delta from this one. We use this. We're going to use this one in partial derivative, right? But this one differential. Now, what I realize is that this one, you give it the full name delta, but it's popular to just call this one del. Alright? Small change. So, r changes to r plus a small change in r, which is r plus del r. Right? As for h will change and become h plus a small change in h, del h. Right? So you see that I'm probably using the arrow would not be appropriate here, because the arrow generally implies that. Right? So let me write the word. This becomes, so r becomes r plus del r, and h becomes h plus del h. Alright, so you see that. Now, here, what would happen to the volume? Well, V becomes V plus a small change in V, del V. Alright? Now, what is that new volume if you consider calculating it? The new volume will be what? Let's find out. Well, we know that the volume is pi r squared h. So V plus a small change in V will become going to be pi times the new r plus a small change in r squared times h plus a small change in h, which is the new h. So we have all of that. Alright? Now, suppose we multiply them out and so on and so forth. This would be equal to pi times r plus small change in r times r plus small change in r times h plus small change in h. Alright. So, what would happen here? R times r is r squared. Is pi times r squared times r times delta. R times del r is r del r, then del r times r is r del r again, so it's plus 2 r change in r. You see that? R times change in r plus r times change in r is 2r times change in r plus change in r squared. So del r all squared, del r squared times h plus del h. Okay, good. So it is equal to pi times. Alright. We're going to multiply out these. Alright. It's going to be r squared times h. So it's r squared h plus r squared times change in h. So it's r squared times a small change in h. Right? Plus 2r small change in r times h. So you have 2r times small change in r times h plus 2r times h, and then 2r times small change in h, 2r small change in r, small change in h, plus, alright, this part now, change in r squared times h, let's call that h times change in r squared, all squared, plus change in r squared times change in h, so change in r all squared times change in h. Alright, you see that? And remember, pi is multiplied by all of this. So let's see how this goes now. This is equal to pi times r squared h plus pi times r squared times a small change in h plus pi times 2r times small change in, well, we have small change in r times small change in h plus then pi times small change, now times 2r times small change in r times small change in h plus, then we have pi times h times small change in r squared plus pi times small change in r squared times small change in h. Alright, good. Have all of that. Now remember, this is volume plus a small change in volume. We'll give you that. Now, the small changes, these take place, right? And we consider it. All right, let's first subtract the volume from both sides in order to get the delta V or the del V, the small change in volume alone, because we're interested in finding out what is the small change in volume. We minus V from the left, this is gone, minus V from the right, but V is the same thing as pi r squared h, right? So this would go as well. So let's make a little change to that. That is gone, and that is gone. Alright, so this is all we have left. So all of this is a small change in volume. Now the thing is, the change in radius, del r, and the change in height, del h, are small. Now let's keep those. But you see, when you have small times small, it becomes even smaller. If you have small and you square small, it becomes even smaller. Now let us just neglect even smaller changes. What I mean is this: you have a small change in volume is equal to pi r squared by small change in h. Let's keep that. That's pi r squared, that times a small change in height, good, plus, all right, here you see this small change in r multiplied by small change in height. Let's get rid of that. Very, very small. So let's ignore it. And in fact, this here would not be an equal sign. It would be an approximately equal to sign. It's not exact. We're weeding out all of the much smaller changes. Small change in r times small change in h. That's very, very small. Just ignore it. Now we have here small change in, well, we have pi r squared times a small change in h. We have 2 pi r h let's see, 2 pi r h. I didn't write this. 2 pi r h times small change in r. Alright, I didn't write this down, my mistake. This should be, we have pi times this, pi times that, and then this will be somewhere here. Alright, so we have pi times r squared h, which we erased, then pi times r squared, changing h. Alright, then pi times 2r h, changing r. So this should have been somewhere here. Alright, no, we would not get rid of this, so we have 2r h times small change in r. All of them that has change in h alone or change in r alone, we keep them. Anything that has change in h squared or change in r squared or change in h times change in r are much smaller. It's like you have 0.1, it's small. You multiply 0.1 by 0.1, that's 1/10 by 1/10 become 1/100th. Much smaller, right? So we're getting rid of all of these changing r or changing h that are squared. This is squared, so get rid of it. This is squared, so get rid of it. Alright, so this is what we have left. Right? What we're doing is deriving a certain equation here. Now, what this is saying is that a small change in volume, right? Well, why did I write this approximately equal to like this? It's generally written more like this, right? The curve is at the top. Is approximately equal to, but hold on, pi r squared is what? What did we get? How did you get pi r squared? Is delta v by delta h. So this is delta v by delta h will give you the pi r squared, and you multiply it by a small change in h plus, alright, 2 pi r or 2 pi r h. Yeah, I had skipped this out. You have brought down the 2, the pi multiplied, the h. But what happened to the r? I should have written the r here, you know. My mistake again. It's 2 pi r h times a small change in r. So how did I get the 2 pi r h again? Let's see. Change delta v by delta r. Give that. So delta v by delta r times a small change in r. Alright. So here we have change in volume is approximately equal to the derivative, the partial derivative of volume with respect to height times a small change in height plus the partial derivative of volume with respect to r times a small change in r. Alright, so this is a certain equation that we'll be using, not just apply as it applies to cylinder, but other things as well. So we'll continue talking about it in one video.